Hello, this is reading quiz number 28, which is all about Riemann sums. We studied a little bit about Riemann sums in the lab, and this whole unit will be driven by the question of how can we find area underneath a curve? And the area underneath a curve, we'll find out, is a very useful concept that can be applied to a lot of different fields. So, we're going to start out with the basics in this reading quiz. A little bit of a background. This unit is driven by that idea. Can we find the area of any shape that is defined by a particular function? And we've seen that this sort of problem for many years. One of the more famous people who tried to solve this problem of how to find the area of a circle is Archimedes, and one of the techniques that was used was called the method of exhaustion, where regular polygons are inscribed inside the circle, and then the number of sides is increased, and as the number of sides increases, then presumably the area approaches the area of the circle. So you have to keep on going from an 11-sided polygon, regular polygon, to a 12-sided, and so on. We're going to use a similar technique, or at least idea, but we're going to fit rectangles between a function and an axis to approximate the area. So we're going to stick with just the rectangles for now. The more rectangles that we use, the more our approximation will approach the real value. And we'll go into more depth tomorrow, talk about infinite number of rectangles within a particular interval. But for now, we're going to use a finite number of rectangles. So let's start with an example. We're given a chart, and the chart has specific values for f of x. And we want to use a right rectangle and a left rectangle approximation to approximate the integral from 0 to 15 of f of x dx. This integral sign we studied in the lab. So here's the idea. In yellow, I've got little dots to represent the function's height at the given values, x values in the chart. The first one we're going to do is a right rectangle approximation. And if you'll remember, what that means is the right side of the rectangle will touch the height of the function and will go across. So just as the easiest one to see here is that at 8, 8, we see our function has that height. And that extends backwards, starting from 5 and going to 8, because 8 would be the right side of the interval from 5 to 8. And so our height of our rectangle is 8 there. Our height of our next rectangle is -7, and then our last rectangle would be 9. So, as I just said, we need to take a look at the heights and widths of each rectangle as we go along. So we're going to start with the right rectangle sum, and we're going to make sure that we use our table to explain where we're going to get our values. Don't just throw out values without any explanation for where they came from. So this integral is approximately 2 minus 0 times f of 2. So the width of this first rectangle and its height is f of 2, the right side of the interval from 0 to 2. And then we've got a rectangle from 2 to 3, so that'll be a width of 1 times f of 3. Rectangle with a width of 2, so that would be 5 minus 3 times f of 5. 8 minus 5 times f of 8. 11 minus 8 times f of 11. 15 minus 11 times f of 15. And presumably, finding the areas of these rectangles will give us a good approximation for what the area underneath this function is. And remember, we talked about in the lab that sometimes we get rectangles that are below the axis, and that would be what's called negative signed area. And we're going to account for that by the negative height values that we have. Okay, so it's possible that our answer to this particular integral is going to be negative. It's certainly possible that it's positive. It's certainly possible that it's 0. So we go through, we plug in our values. F of 2 was 1, f of 3 was 4, f of 5 was -2, f of 8, 8, and so on. We plug them in and we do the arithmetic, and we get 41 as our approximation. If we do a left sum, what's changed is that the left side of the rectangle determines the height. So as opposed to the previous example, as you see here, the first rectangle's height was 1 because that was the height of the right side of the interval from 0 to 2. In this case, the left side, or f of 0, or 7, is going to determine the height of this particular rectangle. So the rectangle looks different. Notice also that we're not going to use our right endpoint because that's the right-hand side of the interval. It's never going to be the left part of a rectangle. Similarly, on this particular diagram, you see that the leftmost endpoint was never used in the right rectangle approximation. All right, so again, make sure that you cite the table, and by that I mean that you make sure that you say that you are finding f of 0, f of 2, f of 3, and so on. The widths of the rectangles are the same, 2 minus 0, 3 minus 2, 5 minus 3, etc. Those are the differences in our x values. But our heights are all going to be different. In this case, f of 0 is the height that determines our the height of our first rectangle. F of 2 will be the second one, and so on. We use our chart, we plug in our values, we do the arithmetic, and we get 13. Notice that those two values are not even close to each other. Part of that is because we're not given very much information about the function. We have lots of big gaps in these intervals, and so yes, our approximation will be off by a little bit. Here's a second example. Use a right rectangle, left rectangle, and midpoint rectangle approximation with 5 rectangles to approximate the integral from 0 to pi over 2 of cosine of x dx. Okay, so the area underneath the curve, the signed area underneath the curve cosine of x. And we notice that they don't give us a table to start, although you can see it on the PowerPoint. Whoops. So we'll need to create tables that will help us with our approximation. And we'll need 5 rectangles for each approximation that we do. Some of them will just be left endpoint approximations. All right, so the first one, if we use the left endpoint approximation, would start at 0. And then a fifth of the way through the interval would be our next one. So we would actually use pi over 10 for our next approximation there. Then pi over 5, because that's 2/5 of the way to pi over 2. And then every other one beyond that. The midpoint approximations we'll see are going to be the ones that use the pi's over 20. So each approximation we'll do on a separate slide. Right rectangle approximation. All right, we're going to approximate the integral from 0 to pi over 2 of cosine of x dx. With 5 rectangles, okay, that means the first one will be a fifth of the way down. So a fifth of pi over 2 is at pi over 10. All right, so then we're going to go every fifth from then on. So we need to go from a fifth to 2/5 of the way, to 3/5 of the way, to 4/5 of the way, to 5/5 of the way, which is all the way. So 2/5 of the way, we would add another pi over 10. Well, pi over 10 plus pi over 10 is pi over 5. So notice that's this one here, and we're going to skip every other one in this particular chart. Then we're going to add another pi over 10. When you add pi over 10 to pi over 5, you get 3 pi over 10. And then we get 2 pi over 5, and then finally pi over 2. So we're dividing pi over 2 into fifths. And every fifth, we're going to find the cosine value and use that as our height. The width of each of these intervals is going to be the same in this case, since we're using even width. That was given at the start of the problem. And in this case, that would be a fifth of pi over 2, or pi over 10. Okay. When we work this out, we can use our calculator, and we get 0.834. If we use a left rectangle approximation, same principle, we're going to divide pi over 2 into fifths. And when we do so, we start out at 0, since we're using a left rectangle. And then we'll move forward by a fifth of pi over 2. In other words, pi over 10. Again, we're using that pi over 10 here. Where do you think we're going to go next? 2 pi over 10, or pi over 5. Then 3 pi over 10. Then 4 pi over 10. And then we're done, because we're using the left rectangle approximation, and we need 5 rectangles altogether. So cosine of 0, cosine of pi over 10, cosine of 2 pi over 10, cosine of 3 pi over 10, cosine of 4 pi over 10, and then another pi over 10 gets us to the end of the interval. Again, the width of the interval is, in fact, pi over 10 here. We get an approximation of 1.149. Notice that those two are closer than the one that we did in the previous example, because our widths are smaller. All right, so we don't have as much to deal with. Finally, midpoint rectangle approximation. So each interval goes from 0 to pi over 10, to 2 pi over 10, to 3 pi over 10, to 4 pi over 10, to 5 pi over 10. Okay, those are the middle ones here. So when we do a midpoint rectangle approximation, what we're going to do and what we need is the midpoint x value of each interval. Well, what's the midpoint of 0 and pi over 10? It's half of pi over 10, or pi over 20. So that'll be our first midpoint. And we're going to find the function value at that midpoint x value. The next interval, as you remember, goes from pi over 10 to 2 pi over 10. All right? So we need a halfway in between pi over 10 and 2 pi over 10. And you can work that out and get 3 pi over 20. All right? Another way of looking at that is, if we add a pi over 10, the width of the interval, to pi over 20, that's where that 3 pi over 20 is going to come from. We're doing all of this with our x values. All right? Our first midpoint x value is pi over 20. Our next midpoint x value is 3 pi over 20. The next one will be 5 pi over 20, in other words, pi over 4. And then we continue on. Notice that the width of the interval is just going to be still pi over 10, which is what we got here, right? And that's what we would get if we calculate each one of these. We would get pi over 10, pi over 20, 3 pi over 20, 5 pi over 20, 7 pi over 20, 9 pi over 20. And we get 1.004 when we work all that out and plug in our numbers. I want you to notice that it's not just the average of the left and the right approximations. That will be something else that we'll discover later on called the trapezoid. All right, so 1.004, hopefully that would give us a little bit more accurate estimate than either the left or the right approximation. Don't know for sure in this particular case, but you notice it is right in between the two, which is not always the case. It depends on where the function goes after it passes the left endpoint and goes to the right endpoint of our interval.